Okay, so now we're in a position where we can find the limits of a really broad class of functions, polynomials, very, very easily. All right, so look at this thing. Here's what I'm going to do. I'm just going to apply a couple of some limit properties. Remember, there's a limit property that says I can bring this number out in front. So this is the same as 3 times the limit as x approaches 1 of x. Remember that the first theorem we looked at said the limit as x approaches a number of x is just that number. Well, in my example here, a is 1. So this is just 3 times 1, which is 3. And that's it. I'm done. It's that fast. No epsilons, deltas, no absolute values, right? Try to remember who comes first and who comes second. That's all there is to it. All right, let's look at another one. All right, how about this thing? Look, I'm going to use my properties again. First, I'm going to use the one that says the limit of a sum is the sum of the limits. All right, so let's split this up. This is the limit x approaches 1 of x squared plus the limit as x approaches 1 of 3x plus the limit as x approaches 1 of 1. All right, now remember it was the very last limit property that says if you have the limit of a function to a power, you can just kind of bring that power outside the limit. So this is the limit as x approaches 1 of x squared plus, I'm going to do the same thing here. I'm going to bring that 3 out. This is 3 times the limit as x approaches 1 of x. And how about this one? Remember, this is our second theorem. Our second theorem said the limit as x approaches anything of a constant is the constant. Well, my constant here is that number 1. So this limit is just 1. All right, but now look, we've got the same thing. The limit as x approaches 1 of x is x. And here the limit as x approaches 1 of x is 1. Still plus that 1 on the end. All right, now look, this is just an arithmetic problem. 1 plus 3 plus 1 is 5, and that's it. Right? That's it. There's my limit. Okay? Much more straightforward now. Okay, so now I've got another theorem. All right? And this is going to generalize what we were just doing on the previous slides. Right? If you're taking the limit as x approaches a of a polynomial. And if you want to look back, both of those things that we just looked at, they were both polynomials. To find this limit, all you have to do is evaluate the polynomial at the number. Right? And let's flash back real quick. We had the limit as x approaches 1 of x squared plus 3x plus 1. Right? That was the one we just did. Well, this is saying, look, just put 1 in there for x. And this is, what, 1 squared plus 3 times 1 plus 1. Yeah, that's exactly where we ended up. Right? It's 5. So I want you to think about that for a minute, right? Great theorem here. Polynomials come up a lot, right? This is a really nice tool. If you're taking the limit of a polynomial, just evaluate it at the number, and you're home free. Okay, now I'm not going to actually prove this. The proof it isn't hard. It's just a little tedious. You start with the generic definition of a polynomial: an x to the n, a n minus 1, x to the n minus 1, plus so on down to a1x plus a0. And you want the limit of this, right? The limit of this is x approaches a. All you do is you apply those properties. First, you split it up, right, into the limit of the sum. Then you bring all the coefficients out in front. Then you bring all the exponents outside. Then you have a bunch of limit as x approaches a of x. All those become a's. I won't bore you by watching me walk through all of that. Okay, so now, kind of an obvious next step, right? If r of x is a rational function, right? Remember what a rational function is. A rational function is the quotient of two polynomials. It's p of x divided by q of x. So what this is saying is if you've got a rational function, it's the same thing. It's the exact same thing. Just evaluate it at a, whatever a is, and the number you get, there's your answer. So a whole nother class of functions, right? A whole nother class of functions we can do very, very quickly now. And again, I'll leave the proof of this one to you. It's just an application of that quotient property for limits. Okay. That's it for this lecture. I know, super short. In the next lecture, we're going to look at a bunch more examples. We're going to look at some kind of more complicated ones. See how we can take these two theorems, the theorem for polynomials, the theorem for rational numbers, combine them with all of our properties to find the limits of really a very wide range of functions.